Welcome to the pre-recording of lecture 39 of MCS 481. The next to last lecture in this course on applications, but also on another geometric data structure. So the application goes towards mesh generation. The quadtrees are a data structure which is very useful for mesh generation, but also very useful for the context within this course, in the sense that it is a simple data structure. So what's the problem? What are quadtrees and how are they used for mesh generation? This is the structure of this lecture. Okay, here is a mesh, actually two meshes. At the left we have a uniform mesh, so we have a square and we triangulate this square in all kinds of small boxes. At the left the mesh is uniform. At the right we have a non-uniform one. So if we focus on the green spot, that might be the green square. That might be one spot where you need to work with very small triangles. But it might be that anywhere else on your mesh you are fine with non-fine, with a much more coarse subdivision. So uniform meshes are just, they have a very simple construction, a very simple recipe, but actually they are very wasteful. So even on a very simple example like this, you may have to work either with 128 triangles in the uniform mesh versus only 22 triangles in the non-uniform mesh. So that's already, on this small example, a huge difference in the cost, in the storage costs. Okay, so here is thus the problem. There is a course on numerical PDEs, and their finite elements will be discussed. But a typical application is to solve the heat equation. And why would you need the heat equation for? Well, there is the chip design, so to simulate the heat emissions on the circuit board. So this is a lecture that is aimed towards application. It is not really an applied course, but what we are doing is extremely relevant towards applications. In several numerical PDE courses, one often may take the mesh as given and then go further with describing the methods that use the mesh. In this course, we are actually seeing the methods and the algorithms to construct meshes. Okay, what are the requirements on the mesh? So first of all, the non-uniformity that was motivated on the previous slide. If we are modeling a circuit board where the components are represented by polygons, then we want for our heat equation, we want to have a finer granularity near the edges of these polygons. We want a well-shaped subdivision. So in some sense, meshes are often also generated by Delaunay triangulation. So that is an alternative, well-taken route. Here we start from squares, and then actually we are guaranteed that all the angles are at least 45 degrees or 90 degrees. So we want, so this well-shapedness is already familiar to us from the Delaunay triangulations. So we also want that the edges of the components are actually contained in the triangulation of the mesh. So in some sense, if we represent our objects by polygons, also these polygons will actually have a very particular shape. And then the last property is the conforming property. So if we, and that's actually saying that we have a proper triangulation. So we have actually no overlapping triangles, which means that the vertex of every triangle, it could be shared, but it could not be in any of the interior of the edges. So we will give examples on how to make triangulations conforming. So the subdivisions that we are seeing are very particular triangulations. That's another way to see this. All right, we have been using the software CGAL. Perhaps I have to go to the page that I prepared, or the browser position. So there is the package overview, and you can see that there is an entire section on mesh generation. So there are many applications towards geometric modeling as well. And the other point of my slide is that many of these packages are actually wrapped to Python. So if you are still looking for a topic for a final project, project 3, there are so many things that we couldn't cover. So look into the mesh generations, for example. So that's the suggestion for today. For today, for this lecture, I'm scrolling down. So here you see also the heat method. So I will go into shortest paths and visibility in the next lecture, but you can see also that CGAL is also very much oriented to be very useful in applications. And here is where I wanted to go. So you can see the quadtrees. Quadtrees are a special case of what is called orth trees. So our focus for today is on the quadtrees. But you can see from the documentation that the main application is also again coming from modeling objects. So we have an object that is given by a point cloud. So many points. So when you see them, so it looks like it's a solid surface, but we're actually storing those structures in a quadtree. In this lecture, we are restricted to 2 dimensions, but as you can see, quadtrees are a very special case of octtrees. Quadtrees because we have 4 quadrants in the plane. In 3 dimensions, we talk about octants because we have 8 regions. So there are plenty of examples here. When I was preparing this lecture, I found inspiration for the exercises. So the exercises are not going to be collected anymore in this lecture, but still it's somehow essential that we know that there are activities that will give you a better understanding of the subject. Okay, so that's actually also one of the reasons why software shouldn't actually not really come at the very end of a lecture. So we focus on quadtrees because they are a simple data structure and it fits very well in a self-contained lecture on computational geometry. For the applications, and also here the people who designed the wrappers for Python wrapped 5 packages. So this is another illustration of how important this topic is to applications. It is also a suggestion, if you're interested in geometric modeling, to actually explore this connection in a final project. So Python is relatively easy to use, easier than the C++ code in CGAL perhaps. But there are plenty of explorations to do. So you could start from an example on the meshes, prepare an input, and then process an output with a geometric illustration of what you just computed. Following then also the pattern, the mathematical pattern of this course, what is the complexity of the mesh, and do the algorithms, are they very efficient to reflect the complexity? You can determine that experimentally. But also it's good to understand the mathematics behind it. Okay, so this is the introduction, the problem statement. Let's now go to the definition. What is actually now a quadtree? So a quadtree, the name quad comes from the quadrants. So in the plane we have 4 quadrants, which we here label the northwest, the northeast, the southwest, and the southeast. So this is a subdivision of a square region into smaller squares. So if you want, we always talked about rectangular boxes. You can also see this a little bit in a more general sense. So you could stretch the square a little bit in the rectangular boxes. Then the quadrants would also be rectangular. But we stick for simplicity into square regions that are subdivided into smaller squares. So this slide is not yet a definition. It introduces the terminology, the quadrants, and then the quadtree. It also serves as the labeling of the square regions. Naturally, the trees that are going to come in there will not be binary trees, but they will have 4 trees, 4 children. So this is also where the quad comes from. Okay, so here is the quadtree. I mean, again, not a formal definition, but just to indicate what a quadtree is. So you have, as in any tree, a root, and in computer science, our trees grow from top to bottom. So the root represents the entire big square. So then the big square is divided into a north, east, northwest, southwest, southeast. So the convention of labeling here, you can see that what I subdivided is the northwest region. And then the southeast region is then further subdivided. So the southeast is typically the 4th, and the second one is I think we go from the northeast, south, northwest, southwest, southeast. That might be the convention in the counterclockwise example here. So every node in the tree represents a region. The inner nodes are regions that are further subdivided, and the leaves are the finest part of this subdivision. And it is a recursive data structure, not a binary tree, but a quad tree, where we have 4 children for every node. That is not a leaf. Okay, so now we're ready to do the definition. So how do we construct a quadtree? So in some sense, this is also the introduction to the algorithm. So before we get to the algorithm, we kind of need to make the precise the notation. And what is actually that we want to store? We want to store a set of points. So this is a geometric data science data structure. I was trying to motivate also the course that in this day and age, everybody does data science. If you want to do data science, you need to know about data structures. So this is also the practical relevance of this course. Um, we have data that is consisting of tuples. So typically we just see just numbers in tuples, but numbers are data. So you can also see this as the tuple stored in a database. So numbers can be computed with, so all data can be is actually essentially numericalized. So here you see how the point set is partitioned. So if we want to partition the square, we have the center of the square. So these are the two coordinates. So we can compute the minimum and the maximum in linear time. And based on the coordinates of this minimum, we partition the point in the northeast, northwest, southeast, and southwest corner. That was in the order in which I traversed the four quadrants of the big square. Okay, we keep on doing this until we have at least 2 points in every region. So we keep on recursively subdividing this quadtree. So the definition states that the quadtree is either one node if there is 1 point or less. The empty node is fine as well. And then we are computing the midpoint, and we have the 4 children as is defined up there by the formulas. And we keep on doing that until every point is actually in its own quadrant, is boxed into its own region. Okay, so this is how you would, so this is in the plane, but this is also how you would with an octtree, so kind of a generalization here, define an octtree for points in the tree space. Then you may have to be a little bit more creative with the names of the octets, but the formula follows. Okay, here is the algorithm formalized. So we are working recursively with the base case being that when there is only 1 point or nothing left. So the specification is important as well. So we return the root. So we start by computing the center of the square. And here you see actually now that we think of squares, but it actually shouldn't be necessarily a square. So the algorithm will also work. When every point set, we actually build this box around it for all practical purposes. The coordinates left and right and top and bottom, they actually determine what the midpoint is. Okay, we compute the set of points in the northeast corner. So again, this is a loop through the points, linear in the number of points. We construct the child recursively, so we do a recursive call here, and then the rest is just a repetition. We do this 3 more times for the 3 other quadrants, and then we construct a node. straightforward processing of the sectors. And notice here the inequalities. I leave it up to verify that every point gets in one unique quadrant. So we have often considered points in general position, random point collections. Make sure that also when points have the same coordinates, that they actually land in a unique square. Now they may be at the edge actually, and what is here, this is a more precise definition, and also I should have pointed this out. So it looked, I overlooked this, but the sharpness of the inequalities actually is going to matter if you want that every point has a unique spot. Um, so some of the quadrants are open, half closed. That's also so the southwest corner is a closed. The northeast is actually open, and the other ones are half open, half closed. Um, just to make sure that we have the topology right, and also that the points again are each belonging to a unique square. Okay, what is now the cost? So in each step, we actually have to run through all the points. It depends actually on the configuration of the points. And the critical thing that we want to know, it's going to depend on the depth. Ideally, and that's how we introduced KD trees, we split always in the middle. But so if we there actually we determine our splits on the location of the points. So I will point at the relationship with KD trees a couple of times, but here the cost and the complexity is going to determine on the depth of the tree, and that is going to be determined on the concentration of the points. If you have a point cloud where all the points are actually uh, well separated from each other, you can expect that the depth of your tree is actually going to be fine, that all the points are going to be equally distributed. But if you have points that are concentrated, and you can already think about very bad inputs where your tree is going to be quite deep. So the lemma actually makes this precise. So we consider the distance, the length, we relate here the distance as the length of the size of a square. Then we have the smallest distance between any of the 2 points, and then we have the depth of the quad tree. So you can already see if you're going to generate points, and if you have a very accurate, so a quad tree might not be too good if you have many decimal places in your numbers, so that you can have very small distances between your points. It's gonna be fine, for example, if you know your point locations with only 2 or 3 decimal places. So that's also one way to see the formulas here. So, but there is a precise formula of the depth as the 2 log of the ratio between the length of the side of one square and the smallest distance. So this is a very useful lemma, and the d, the depth of this tree, is actually a very important constant. So this is saying something about the nature of your point set. Okay, There are three steps in the proof of the lemma. How do we get to that argument? So it's a mathematics course, so we need to know the arguments. So every time we go down one level in the tree, we cut the size. So this is where the 2 log comes in some sense. So there is the depth. So at the depth, we actually know how what the size is. Then the maximum distance between 2 points in any square. So in order to be in the square, we actually know this as well. So it's the diagonal length of the square. And then this the square root. So the points, so perhaps I should draw this. So we have a square. And the 2 points, the farthest they can be away from each other is one corner and the other corner. So this is where the square root 2 comes in. We can thus make the connection between the length of the square and the distance between 2 points. And also we are at depth I, and there you can see then where the 2 logarithm comes in. So we have the bounds of the inequalities. Perhaps I won't go through this very great detail, but it works out. And you can also then see that the depth is actually bounded by the 2 log of this ratio, the length of the square and the distance between 2 points in a square. The square root of 2 is responsible for the 1/2, and then the final argument is that the depth of the quadtree is that upper bound plus 1. Okay, so this is the lemma, and the lemma actually provides the value for the depth that can be computed. So you're going to know actually in advance if your granularity of your points, if they can be very close to each other. You can already know, and you can compute this actually when you compute the minimum or maximum. You actually know the depth of your quadtree. So the quadtree is a simple data structure, but you can already see what the vulnerabilities are going to be if you are working with points that are very, very close to each other. With 64-bit floating point precision, we have about 14 decimal places, 15 decimal places, so we can put the points quite close to each other. Okay, the theorem states the size of the quadtree and also states actually the running time. So it's a simple data structure, very good as a first take on mesh generation. Okay, I've mentioned KD trees earlier, and this is something that was pointed out when I read the CGAL documentation earlier in preparation for this lecture. So the quad tree is simpler. It can construct it be faster, so that's an upside. And how faster is this? So that's the exercise. But since this is already one of the later lectures, I can actually say where you can find the answer. So if I scroll down here, so here you see the answer to this exercise, and that was done by the generators of the CGAL documentation. So you can see that an oct tree, and it's going to be noticeable. So if you go into the millions of points, actually the graph is actually, so you're only going to start past 1 million points. So that is the first comparison with KD trees. It's also related to what we have studied earlier. So earlier in the course we studied orthogonal range queries. So this fits into that. Okay, I'm halfway. I'm also halfway my slides here, or more than halfway my slides. So we have constructed a quad tree. Okay, what do we do with this now? Or what can go wrong? Well, here is our first example again. I used this example, picked it quite carefully because I wanted to use it to illustrate another property. So this quad tree is actually an unbalanced quad tree. What it means, if you look at the subdivision, is that you have very small squares. So this is a very small square here, and that is actually a very big square. So you have small squares in your subdivision next to big squares. Uh, Unbalanced comes from the fact that we have here, um, so the dot here represents. Actually, I should probably have focused on the southeast. So the southeast is this leaf here. And this southeast leaf has this big neighbor. And that's 2 levels up the tree. So the definition, when is a quad tree balanced? If any two neighboring squares, they differ at most a factor 2 in size. So in a balanced quad tree, two neighboring leaves differ at most 1 in depth. Um, Balancing, if you took a course in data structures and you covered self-balancing data structures, then you may shrug, you know what? We know algorithms to balance trees. But so the word unbalanced and balanced, they actually make sense, but they're a little bit misleading. The CGAL, well, misleading is also not a good word, but there is perhaps a better word that's grading. Uh, I stole this picture from the CGAL documentation. So here you see a shape, and at some places where the shape is turning or is also has an inflection point, you may want to have a finer granularity. You see what CGAL does. It is going to go uh, subdividing. So here we have again big squares next to very tiny squares. So the grading of quad tree is by subdividing the bigger squares adjacent to the smaller ones. Okay, I'm following the mm, language from the textbook. So here is the balancing of the subdivision, where we subdivide the big squares next to the smaller ones. So now you see that the difference in size, we have a small one, and here we have a very big one, which is 4 times larger. Here we have a small square, but that's now next to one that is only twice. So there is the factor 4 and the factor 2. Okay, balancing a subdivision. CGAL provides algorithms for this. Here is how the trees are now balanced. Again, balancing a tree is different from self-balancing data structures trees, which you may have covered in a data structures course. So this is why grading is a little bit better technology. We actually subdivide the sibling nodes. And now it's also important to remember the order in which we renamed the sectors. Okay, and now you see that any node is actually now adjacent to any other node just by one level up. All right, finding neighboring squares. So if you balance this, so the balancing algorithms, they have to uh, decide if they're actually the square has a neighbor at the same depth. So you can use this structure to compute the neighbor. So if every point is in its own square, to find the neighbors, so we can work recursively. So the cost of finding a neighbor in the balanced quad tree, then this is linear in the depth. So and here again, this depth is d because you may have to go all the way up the root to the tree. I'm sorry, so this is here the algorithm. So the cost of finding a neighbor, so in some sense these are two topics on the same slide. You can use a quad tree to find a neighbor, and the theorem says here, doesn't mention the word balanced. So then this, if the tree is not balanced at all, you may have to go all the way to the roots. Finding the neighbors, this is also something that you need to do in balancing the tree. So here the algorithm is not, so the idea of the algorithm is outlined here. It could be another exercise to actually write it out formally. So the time is limited here. So in this last end of the course, we could spend 3 entire lectures on this topic, but the semester is not long enough. Okay, KD trees, we've seen that they are more complicated, and why did we actually see them so in big detail? Well, the KD tree will actually outperform the finding of the nearest neighbor. So I got this also from the CGAL documentation, and so I think it's not. So there is the nearest neighbors. So here you see. This exercise is thus also already solved, but so this is the last one of the last lectures, so the exercises will no longer be collected. But if you so seeing is believing, but if you actually really do it, then you really know it. So on your computer, see if you can verify this. I suspect that the documentation was generated longer time ago, and it might be that your computer might be stronger than the computers that were used to generate the documentation. Also see here actually that the number of points might not be that large. So million is at the upper end here. Okay. Now, this is also a mathematical course, so provide arguments to justify this statement. Why is balancing needed with quadtrees and why is it not needed with KD trees? So in some sense, in this part of the course, we also often go back to what we've covered before. So some of the questions that we raise here would be very suitable for a final exam, if there is any. Okay, I'm 40 minutes in, so the topic is very interesting. So here we see now the cost of balancing the tree. So this is another theorem. Time is not, we don't have sufficient time to provide formal proofs, but in the statement of the theorem, we see the important value d from the lemma that we have considered a little bit more carefully. So you see again the depth of the tree and also the number of operations that you have to do. As in the previous theorem, we have two important statements. So there is the number of nodes that we have to balance, and then also the search time each time. So the d plus 1 for finding the neighbors, that is important. Okay, one last topic. These are Steiner points. So you will see the Steiner points also when you look at the um, generation of meshes starting from a Delaunay triangulation. So we want well-shaped triangulations. That means that our angles need to be at least 45 degrees. If you say 45 degrees is kind of a restriction that I cannot impose because my polygonal objects they should they can have angles. So the 45 degrees also restricts a little bit the if you're modeling circuits, it might be fine for heat, but it could be that you have objects that are going to have other angles. Then a Delaunay triangulation is very good. So in a Delaunay triangulation, you have the minimum edge that is optimized, that is made as large as possible. If it is not sufficiently large, then you add Steiner points. So here Steiner points are introduced to have a well-shaped edge. So what is shown here is the case where you have a component on your circuit board uh, represented by this fat edge here. Now you can't really add this as an edge because it's an edge of a square and actually only half of it. So you actually need to add an extra vertex. Now you could say, well, I'm going to add the vertex over there, but then uh, the subdivision would not be conforming. So the conforming definition that was a requirement from the beginning, it was that we didn't have vertices at the middle of an edge. So, but we can have vertices at the middle of a square. Actually, we can't, but then we triangulate it. So it's a vertex of our triangulation. And that vertex is called a Steiner point. Okay. Um, So this is then how mesh generation goes, and here I'm actually summarizing an entire lecture. Mesh generation with quadtrees. And of course, there are also in geometric modeling, there are octrees, where one works with tetrahedra instead of triangles. So we balance our tree. So we have our objects on our circuit boards. We want to generate a mesh for that. We make a quad tree of sufficient depth. We balance it and we triangulate it, adding Steiner points when needed. So in 3 steps, kind of a overview, very coarse overview of this topic. Now, the cost of this mesh generation can be made precise with the quantities u and the perimeter. And it is linearly in the sum of the perimeters of all the components, and it is logarithmic in the length of the size of the square. Again, this logarithmic will be 2 log from the proof of the lemma, but the order is just the same. Okay, conclusions. So we have considered triangulations before in this course. We started with polygons, and triangulating convex polygons is very straightforward. By triangulating y-monotone polygons, we reduce to that case. So this is how triangulations of any polygons appear naturally. Delaunay triangulations are angle optimizing triangulations, and this was also already motivated by geometric modeling. We could get Delaunay triangulations also from Voronoi diagrams, and these in turn can also be obtained by convex hulls. So in some sense, I hope that all the notions, the geometric concepts and algorithms are starting to get somehow in perspective. Here is a summary of the focal point in this course, in this lecture was on quadtrees, which can be used for mesh generation. Quadtrees are very attractive because they are good, good and simple data structure with very precise and yet simple bounds for the generation, so the construction and the balancing. And then from that we have the mesh, which depends on the components that we want to model. Okay, I will stop here. So this is the next to last lecture. In the context of this course, it is important that this is another data structures lecture, very important for data science. Towards the final project, meshes are extremely important, and with the Python bindings to CGAL, I hope that there is ample opportunity for a topic for a computational project.